Okay, welcome everyone to this TCS Jagiellonian seminar. So today, this academic year, our first speaker will be Grzegorz Gutowski from our group. So who is a researcher, permanent researcher in this TCS group, and he will talk us about one-sided local crossing minimization. Please.
Thank you. All right, so I will be kicking off the TCS seminar this year. Everybody was hoping for a presentation by Bartek, but he will have to leave with me. Okay, so this is this research I will be presenting is a joint work with Martin Loeffler from Utrecht University, with Yuto Okada from Nagoya, and Sasha Wolf from Würzburg. And this will be about drawing graphs. And some motivation for this research is constructing such drawings. And there's this heuristic approach to producing such drawings that look kind of nice. That is called Sugiyama framework. And in this framework, we want to produce a drawing of a graph which is not planar, so you can't expect to have crossing-free drawing. And you are drawing vertices. These are these white boxes on the drawing in layers. So this is the lowest layer with two vertices. There's next one and next one. And there is some heuristic that tells you where to put these vertices. Sometimes the graph is directed, and direction of the edges somehow tells you which vertices should be higher or lower in the drawing. And we don't focus on that. And this particular drawing is orthogonal, but for today's talk, this won't be important. Okay, so this Sugiyama framework somehow first, I already said that, assigns vertices to layers, but then has to decide inside each layer the permutation of the vertices on that layer. And choosing right permutation can give you more or less crossings. And today we will focus on this kind of decisions. How do you order vertices in one layer so that you don't get too many crossings? Okay, so we will focus on situation like this. We have some two layers and something that we call two-layer network, but it's just a bipartite graph. There are vertices X that has to be drawn on the upper layer, and vertices Y that has to be drawn on the lower layer, and there are some edges, and you can focus on different metrics of the niceness of a drawing, but we will focus on disliking crossings. So if we only care about crossings, which edge have a crossing, somehow this drawing combinatorially boils down to deciding the orders, right? Because two edges cross if the endpoints are in different order in the order on X, then they are in the order on Y. Yes. Somehow these orders simply describe which edges cross each other. I will keep drawing the vertices in the layers, but you can simply ask questions about orders and don't draw it at all. Okay, and how does this two-layer drawing problem relate to Sugiyama framework? Again, there's a heuristic there that first tries to decide orders of layer 1 and 2. So you just focus on first two layers and somehow optimize the crossings there. And then second layer gets fixed and you extend it to the third layer by, again, just looking at layer 2 and layer 3 and looking to optimize the crossings there, and you keep doing that with consecutive layers until you get to the last one. Hope that this somehow greedy approach of extending layer by layer gives you something that is not too bad compared to the optimum solution, whatever that optimum would be. Okay, so the classical approach would be to simply minimize the number of crossings in total, and this problem is called two-sided crossing minimization. And yeah, you have a two-layer network on input and some parameter k that would be the maximum number of crossings that you allow, and you would like to output a drawing. So these two orders and have at most k crossings, or you can focus on decision problem. Doesn't really matter for this. So the problem is NP-hard, even if this bipartite graph is a tree, and it was known to be FPT in K for a long time, and I have just learned yesterday that there is some breakthrough there that will be presented on SODA. So there are really fast FPTs, so sub-exponential in K. And yeah, so this is the what happens somehow if you want to run this heuristic of constructing layer drawing in the first step. Yeah, you have not a really bad situation. Yeah, you can do the first step, and then every next step is this situation where the previous layer is already arranged, and you want to find a good arrangement of the good order on the next layer. And this problem is called one-sided crossing minimization. And here the order on X is prescribed, and you only look for the order on Y. And for the complexity, it's also NP-hard, even on trees. And it was the topic of PACE challenge last, not this one, but the previous one. And good FPT algorithms were known for some time, and it looks like they were easier than in the two-sided setting. Okay, so this is the landscape in the classical optimization of crossings. But today I will focus on a variant where we do not focus on the total number of crossings, but we would like to bound the number of crossings locally, and the way to do that is to bound the number of crossings on a single edge. Yeah, so we would like to find drawings such that any edge has at most k crossings. Yeah, so some argue that this is a better measure of how bad the drawing looks like, and this whole business is called k-planarity. And we say that that a drawing is k-planar if each edge in the drawing has at most k crossings. So yeah, this is somehow local version of the optimization. It's generally hard, and usually the local this local variant looks harder than the general one. Somehow, yeah, we'll see that. Okay, so we can define the local version of the problems, and the first step we have both first and the second layer free, and we look for a nice drawing. And the bad news that it's not only NP hard, but it's also hard in terms of FPTs. Yeah, this is very hard in terms of FPT algorithms, and yeah, somehow this is the landscape I'm interested in. And there's one-sided version of the problem, and there we have FPT algorithms. Yeah, so it looks like one-sided version is simpler than two-sided for this local crossing minimization. And yeah, it is where we started this research, and I want to show you two results. One is kind of expected, and it was that the problem is NP hard, but somehow the proof was lacking, and we fixed that and give a proof that this problem is indeed NP hard. But on the positive side, we give some approximation algorithm, and before there was no approximation algorithm known, and we are able to show a free approximation with some nice ideas. We also show that these ideas cannot beat this constant 3, but it's a very nice problem to look for better approximations. Our hardness proof does not disallow any, does not give us any approximation hardness. So it could be possible that this problem allows for much better approximations. Okay, any questions before?
You mentioned FPT, but it was known before knowing that it was NPR.
Yes. So yeah, there is a previous paper that shows NP hardness in the weighted case, whatever that means, and gives FPT and conjectures NP hardness even when the weights are somehow not necessary to prove hardness. Okay, so let me first entertain you the approximation result, which is maybe positive, and in the end I will give you some ideas for the hardness proof. Okay, so what will happen is that we will use something called median heuristic, and this median heuristic was used for the global crossing minimization. And the idea behind the algorithm is to simply, for each vertex in the y part, the x's are already in some order. Yeah. So each element of y can look at his neighbors in x and pick the median one. Yeah. Somehow I want to be in the middle of my neighbors, and this looks like a good place to be. So the median heuristic simply tries to draw each vertex below the median neighbor, and it requires some tie breaking. Yeah, so there are many vertices that share this median, and you have to decide in which order you draw them. And this, so they showed a particular tie-breaking scheme that allowed them to show three approximation for the global crossing minimization. And what we do is we define a different tie-breaking scheme, more involved, and are able to show that this modified heuristic is also a free approximation in the local variant. And let me show you how this works. So before we proceed, I have to do some preparatory cheating, and I have to define what is median, because for vertices of odd degree, it's clearly the middle one, and for vertices of even degree, you can choose. And I think in the original version it didn't matter. I think they were all rounded down or up. It's all the same. We have to do something more clever. And it's important for our proof that vertices of degree 2, so say this one, choose the right edge to be the median. I will always draw the median edges red. And for the vertices of even degree, but at least 4, they will round the median down. So each vertex, say of degree 4, like this one, will choose the second neighbor from the left to be the median. Okay, so we have to be careful about choosing the median. And then we can, when we do that, we can define the tie-breaking scheme that is drawn in this example. So the tie-breaking scheme is to first place from the left the vertices of degree 2 and order them so that these blue edges are also go to the left. So we order these vertices in order of their neighbors, the second neighbor, yeah, because now I'm ordering all the vertices that have the same median, yeah, and this is this median vertex. these are the median edges. This is the order of vertices of degree 2. Then we put the vertices of odd degree. And here we don't care about order. We can place them in any order. And then in the end we place even degree vertices of degree at least 4, and we draw them in order of increasing degree. Yeah, so it's not coincidence that this vertex of degree 6 is after vertices of degree 4. So this this median and tie-breaking scheme is more complex than the previous one. We are not sure that it's really important, yeah, but somehow this tie-breaking scheme allowed us to do the proof. Okay, some more definitions. For each 2 vertex, there's this median edge that goes to median, and the second edge is called the heavy edge, and they will be the most problematic in the proof to somehow handle those blue edges. And these edges that are neither median nor heavy are light edges, and they are the easiest in the proof. Okay, so this describes the algorithm. Yeah, I simply calculate medians. For each vertex, I draw its neighbors that choose him as median in this order, and this gives me an order on Y. Any questions? Okay. So now we will have to prove that that each edge has not too many crossings, and somehow the main technique is to have some crossing counters, and when we look at an edge and a subset of vertices in Y. Yeah, so I select some subset of vertices in Y. I simply count the number of crossings of edge E with edges that have an endpoint in Z. Yeah, this will allow me to somehow divide Y into pieces and calculate the crossings somehow given by subsets of Y independently. And yeah, somehow this is trivial that if you calculate the crossings induced by 2 subsets, say this joint, you simply sum the crossings given by 1 subset and the second subset. And what we are really interested is somehow if there is some optimum order on Y such that the number of crossings on every edge is at most k, then we want to have at most 3k crossings, given by our algorithm. Okay, and this is simple, just a notation. So we'll start by bounding the number of crossings on the median edges. So so there are some simple observations. The first one is that no two median edges cross. This is, yeah, somehow this is the vertex, and these are the median edges of this vertex, and the neighbors are drawn here. And if there's a next vertex, all the median edges going there, but they will be drawn on the right. Yeah, this is somehow the median heuristic even without tie breaking. So we don't have crossings between red edges. And now we want to calculate the number of crossings with other edges. And we divide it into subsets. We split Y into subsets. And first we calculate the crossings with edges that are not on this picture, so that are from vertices that have different median. And first thing is that each such vertex contributes the same number of crossings to all the red edges in this batch, right? Because if this edge crosses one of them, so say it crosses from the left, so yeah, it means if it crosses this one, it has to go here, and then it crosses all of them. Okay, and the other thing is that this number is optimal. So this median heuristic minimizes over all possible orders the number of such crossings. So and this is maybe easy observation. So here is one of such median edges, and some other vertex gives me a crossing on this edge. But because this vertex has a median to the left, yeah, it's not on this picture and is to the left, so it has median to the left. And because of that, this vertex in any other order either is on this side and gives the same number of crossings to this edge, or it's on the other side. But it gives at least the same number of crossings. Yeah, somehow we use the fact that this vertex, this edge is not the median edge; it's on one side. Yeah, so flipping the order between this guy and this guy can only increase the number of crossings given by this vertex to this edge. So somehow we don't care about crossings with other edges that are not on the picture, because we do as good as possible. No other order can improve.
Here you wrote it to the left, on the right with the wrong, like you have this rounding down choice that you do for really more than 4 vertices.
Somehow, if you switch to the other, you always give the median edge starts to cross. So you always, sometimes you don't increase, but you never decrease the number of crossings, because the median is this guy that didn't cross but now starts. Okay, and now now we focus on crossings that we see in this picture. And the first thing is that somehow the odd vertices, they do not matter. Yeah. Wherever I put this guy, in the beginning, in the end, it always gives exactly one crossing to every other red edge. Yeah, because it gives the same number to left and to the right. So somehow these guys do not contribute really, because it's always the same number of crossings. And putting them in the middle, we'll see in the moment, is the best choice because they get as few crossings as possible if they are in the middle. Edges from vertices of degree 2, and this is where our cheating on definition of median plays role, they only contribute crossings to the left. Yeah, so somehow they will only cross each other. Yeah, the blue edges only give crossings to these guys. And again, we can say that this is optimal because in any drawing, one of those three guys has to be the first one. Yeah, and he gets at least these two. Yeah, so no order can do better than that. And for these guys give more to the right than to the left by 1. So again, it's beneficial to put them on the right because every other edge here is happy about that decision. They get less crossings if we start putting them here. And the last thing is that we have to think what order on these guys is optimal. And here it's an easy, greedy proof that, well, putting the guy who has the most crossings last is the best idea, because then you somehow kill all those. Yeah. So this is the proof that no other order can have fewer crossings on the red edges than we do. And yeah, basically for median edges, we are simply better than optimum, or no worse. Okay, so these are median edges, and they were quite simple. Light edges are even simpler. So this is a light edge, and it has some crossings with the black edges. And because this is a light edge, there is a median edge here, and the degree is at least 3 of this vertex. So there is partner edge on the other side of the median. Yeah, and it doesn't matter if edge is on the right or on the left. We can simply flip this drawing. Okay, so the drawing looks like this, and the observation is that every black edge that crosses our edge can either cross the median edge also, or if it doesn't, it has to end somewhere here between this point and the median vertex. And yeah, so to bound these edges that cross our edge and also the median edge, we already bounded the number of crossings on this edge by k. So we have at most k of them here. But now we have to find a bound on the other crossings, and for that we can see that there's this green V in the drawing, and this green V in the drawing is it looks the same in any drawing. Yeah, it's just 3 vertices. These two, the order of these two is fixed, and this one has to be somewhere in the drawing. And we have these edges here on the top that have one endpoint inside V, and the other endpoint has to be somewhere. Okay, but it will cross either this edge or this edge in any drawing because it has to escape V. So in total, there are at most 2k such edges because of the optimality of this other order. So in total, we get at most 3k crossings on a light edge, and this is simple. And the last thing is to solve the heavy edges. Yeah. So now E is a heavy edge. It has a median edge F here, and yeah, somehow there should be some nice proof similar to the previous one, but we didn't find it. So instead, we just tried calculating everything possible. And to do that, I divide the vertices in X into, I have these 2 vertices, W and X, and I just have subsets of vertices that are before W, between W and X, and after X. And in the lower part, I have P and P prime and Q prime. The primes are the vertices that are flipped in the optimum order. So I draw this optimum order here, and in this optimum order, P and Q prime is on the left of Y, and Q and P prime is on the right of Y. Yes, this is well defined. And now I simply count the number of different edges. So this CAQ would be the number of edges with one endpoint in A and the second endpoint in Q, etc. And if I write down all those numbers, I can get some inequalities based on the fact that this order has at most k crossings on E and F. Yeah, and if I look at E, so any edge from A to Q crosses E, and similarly, any edge from B to P also crosses E. Yeah, so these are inequalities that I get simply by counting the crossings on E and F in the optimum solution. Then this is not enough, and I have to somehow use some facts about my algorithm. And the first thing is that it's important to bound the number of A Q prime edges. Yeah, so any edge that starts in A and goes to Q prime, I will have to somehow bound the number of these. And it's kind of difficult because these edges here are on this side, and I don't count them because they don't contribute to the crossings of either E or F. And the way to do that is to use that we deal with that this order is a median order. So the thing that I can see is that any such edge has endpoint here, and this endpoint here has the median either in X or to the right of X. Anyway, it's not a two vertex, right? Because if it's X, it's not a two vertex because I had this order that disallowed blue edges to cross. And then I can simply say that if it's a two vertex, then this median is to the right, or it's a heavier vertex, and then it has more green guys on the right than it has on the left. Anyway, I can bound AQ prime by number of these edges, which is CQ prime. And I can simply construct and this is still not enough because there is there are some more types of edges that are difficult to bound, and we need to bound the number of EX P prime and CP prime. And it's a very similar argument to the previous one. We again have to use the fact that the median edge is somehow to the left of this median edge, and this allows us to calculate the number of crossings. But now it's a little bit. There are a little bit more choices for these edges that somehow balance our crossing edges. But it's a similar kind of argument. And these things together allow us to give a bound. So if we calculate the number of crossings in our algorithm, these are the constants, and yeah, somehow these guys without prime are easy, yeah, because if the optimum order does not change the position of this vertex, they are the same. Yeah, they still give me crossings on E. But for AQ prime, we used this, and CQ prime. CQ prime is where's CQ prime? CQ prime is here, so CQ prime is easy to bound. And the last thing is all these second case are somehow counted by the crossings of F, but we need constant 2 here, so we have to use this inequality twice to get a bound of 3k. And that's all. That gives a proof of free approximation, and it does not at first sight look very difficult, or it looks like this light edges could be improved with some more clever approach. Somehow I could get more inequalities here and maybe improve something. yeah, it looks like only BP prime is really tight in this linear programming. But the bad news is that that we have an example that, and a very simple one, that any median heuristic has to is no better than a 3 approximation. So let's see this example. We have only 3 vertices in the bottom, and we devise the yeah. So these are the median edges, the red ones, and the thing is that this vertex here has a median here, one neighbor here and one neighbor here, and the other 2 vertices, each of them has 2k plus 1 neighbors, and somehow goes k to the left, k to the right. And the choice of position for this vertex is really really bad. Yeah, this edge crosses k edges here, k edges here, and k edges here. So in total, it's 3k. And every other edge crosses only k vertices. But if we take this vertex and draw it here, this edge will still cross only k. The median edge will cross this k, and this edge will cross also only this k. So the optimum solution has only k crossings, and somehow it's very unfortunate for median heuristic to choose position of this vertex here. So bottom line is you have to have some new ideas to get a better approximation than 3. Okay. Any questions to the algorithm or example? Okay, so the other result in the paper is the hardness of the problem, and I've decided not to give all the details because there is some calculation of the constants. I will just give you the ideas. So the reduction is from 3 partition. So we have some numbers, and we want to divide them. So we have, say, 3n numbers, and we have to divide them into n groups of size 3, so that each group has exactly the same sum of the 3 numbers. And the idea how we can use local crossing minimization to encode such problem is the following. So we have these black V's, and there will be more of them, like n such V's, and each such V will have a lot of red crossings with red edges here, and some crossings with red edges here. And it's designed so that they go in the same order. So if I have a lot of crossings on this guy, I have fewer crossings on this guy, and these numbers always are the same. And as I go to the right, each such V somehow encodes that well, this guy can have some crossings. The next guy here can have a little bit less. Yeah. And to the other side, if you look at crossings on this guy, the next guy can have a little bit less. Yeah. And combining that, I somehow decrease the number of possible crossings to the left and to the right, I get something like I have to put here some vertices that have exactly some number of crossings on this guy and this guy. This will be the same, right? And this allows to encode free partition, because I will have some blue vertices here. Each of them will have the number of edges encoding the number if in free partition, and this whole construction somehow asks if you can put these vertices in those places between the V's, so that the number of crossings given by these guys in this area is exactly some number. And by making sure that free partition has some nice properties and the numbers are not too big, not too small, we can control this idea so that it all adds up to a hardness reduction. Yeah, but free partition is not really approximation hard. So I don't think that this proof can give us any approximation hardness. Okay, so let me finish by asking some questions. The first thing is that we would like to have a better approximation. It would be interesting because it have to be different, and there's no reason to believe that 3 is so best possible approximation. And the other question that I find interesting is to try to repeat this for 3 layers. We can go back to how this Sugiyama framework used these algorithms. So somehow you used this two-sided to construct ordering on the first 2 layers. Then you can use one-sided version to somehow find this one. Okay? But then, if we had some if you had some algorithm that could re-optimize this layer, this could be used to somehow, we use these two to give some heuristic optima on this layer, but then we could somehow use the top layer and the bottom layer to re-optimize choices in the middle. Yeah, so instead of just going up, we could somehow change this one. And the problem that would encode this idea is, say you have 3 layers, 2 of them are fixed, and you are to optimize the middle one. And this might be interesting. And this Soda paper that I mentioned also says something about optimization of 3 layers, but there all orders are free, so you can optimize all 3 orders together and get some FPT results. I think it might be interesting to see. In particular, this approximation algorithm no longer makes any sense, right? There is no notion of median vertex, because your median in the bottom layer and your median in the top layer might be completely different. So you have to look for some other ideas to solve something like this. Yeah, and that's where I'd like to end. So if you have any questions, please